Having a look now at unknown sample A, you should have at least seen unknown sample I. You should have at least seen unknown sample A. Let's go through the data and figure out what this molecule is that we're looking at. Starting with, as usual, our unsaturation test. The orange color remains, so no change with Br2, therefore no alkene or alkyne. So we know that there is no double or triple bonds in the system. We're just dealing with single bonds. Or at least with between carbon and carbon in this particular case. We have an oxidation test, and we're told that the solution turns green. It has changed color from yellow, so it has reacted. That means there is something that can be oxidized in there. So I say there is an oxidizable functional group. So we've got an alcohol or an aldehyde. Either of these can be oxidized under these conditions. Last test, we are told that the carboxylic acid test is negative. And I know that it's negative because there were no bubbles. If I saw bubbles, I would expect that for a carboxylic acid. So we simply know that that functional group is not present in this particular structure. Moving into our IR spectrum, as per usual, which should be used to me doing this by now. I'm going to ignore the fingerprint region and just focus on the rest of it. What I can see is I have a strong, sharp signal at about 1720 or so. So strong, sharp signal at approximately 1720. And if I have something coming up at approximately 1720, that is most likely a carbonyl. And a carbonyl, of course, is our C double bond O. There we go. You'll be able to type it eventually. So we know that we've got that sort of double bond somewhere in there. Note that I can't tell you if that's a ketone, an aldehyde, or a carboxylic acid. I just know that the carbonyl is present, or an amide even. I just know it's there. I can rule out carboxylic acid from earlier because it wasn't in my wet test, but I can also rule it out here if I wanted to look for things that are missing. A carboxylic acid would have a big rough signal about there in the 3300 region. Clearly doesn't, so that would double down on my no, there was no carboxylic acid present. The only other thing mildly of interest is at about 2900. I would call that a medium signal. It's not particularly much of anything. Relatively sharp at about 2900. And like all of my organic molecules, that's just telling me I have CHs around. Nothing particularly to gain from that. Coming down to my mass spectrum, just clear that screen. What can we pull out? Well, I have a molecular ion of 58, which I can confirm as that signal here. I can see that in that region, there's no 1-to-1 peak, that's 2 away. I don't get that kind of arrangement, nor do I have a signal that's, say, about a third of the height, 2 mass units away. Importantly, what I'm saying there is that I don't see any halides. I'm not seeing chlorine or bromine present in my mass spectrum. If I was to go into the fragment, I can see a signal at about 15, which is pretty typical of a methyl group. I can see a signal 14 units higher at about 29, somewhat typical of an ethyl chain. And then I have my molecular ion at 58. So I could figure out what the rest of that fragment is, but really I'm not getting much from this other than maybe that there's this aliphatic chain, at least a methyl, if not an ethyl, somewhere in there. But I wouldn't spend too much time on the mass spectrum. So the main things I'd pull out, 58 mass per charge for the molecular ion. maybe CH3 at 15. And my ethyl at about 29. And I could add in that there's no chlorine or bromine in that mass spectrum. Nothing overly exciting, but yes, I could probably pull that information out as well. So now we're going to move on to the NMR. At this point, I don't have a lot. I simply know that there's a carbonyl around, there's another carboxylic acid, and there's no halide. But by the time I'm done with the carbon NMR itself, I'm actually going to be able to say a lot, even before I go anywhere near the proton NMR. Having a look at my carbon NMR, I can tell you that there are 1, 2, 3 carbon environments. I can tell you that one of them is quite high up, about 200 ppm, which is quite common for ketones or aldehydes, and that then 2 of them are quite low down. So only the one at about 200 is interesting, telling me I've got probably a ketone or an aldehyde. With 3 carbon environments, if I presume for a moment I don't have any symmetry, I can only put the carbons as such. Theoretically, I'll draw a more ridiculous example. I could put them in a triangle like that. And in a moment, I'm going to erase that example as I prove it to be false. But the most common way to put these carbons with just 3 of them in their own environments is as a nice simple chain. After that, I knew I had a carbonyl, which told me that, well, my carbonyl could either be here, or I'll draw this example over there, here or here. So I have 3 possibilities for my carbonyl. The left 2 examples are ketones. And as you can see, they actually have symmetry down the molecule, which would mean that these carbons would actually be in the same environment. So there'd only be 2 carbon environments for those ketones. However, this aldehyde, with its lack of symmetry, has 3 carbon environments. And indeed, if I go and look at the molecular weight of that aldehyde, I'll find it's about 58. So even before I've left the carbon NMR, I have a very likely guess that I am dealing with propanol. Let's put all this data in before we go and confirm that with the proton NMR. So I got 3 carbon environments, one at approximately 200 ppm, ketone or aldehyde. I have 2 in the 0 to 40 region, which is likely what we call aliphatic, which simply means I'm dealing with an alkane or an alkyl chain, so I'm further away from things that are electronegative. And lastly, before I even moved on, I will put this gas in and say that the symmetry of any 3 carbon ketone would only have 2 environments. So likely aldehyde at this stage. Now let's let that fix my spelling for me. But I know that, okay, I've probably got that aldehyde. I'm now going to look at the proton NMR to help me confirm that a little bit. Note that I often start taking guesses early on to see if I can work with that. Just be careful not to use confirmation bias and look at your proton NMR and presume it must be this aldehyde. I'm simply saying at this point it's very likely. Looking at my proton NMR, starting off with my signal all the way up near 10, it's almost 9.5 ppm. You tend to only get signals there for aldehydes. So I already said a moment ago that an aldehyde is very likely. This is helping me confirm that. That yes, a signal that high, typically associated with an aldehyde. I can also tell you from this fragment, okay, I know I have an aldehyde. 1 carbon away from that, I likely have something that is resulting in a triplet, which is the coupling that I can see there. And the most likely version of that is some sort of methylene, some sort of CH2. Again, this does look like what I've drawn earlier, but I want to keep that presumption away to say, well, that's the only way I can explain that signal. An aldehyde with two hydrogens next to it. My next one down, about 2.1 ppm. It's quite low, but nearish something electronegative. It's not bound directly to, say, for example, an oxygen or a nitrogen, but it could be bound to, for example, a carbonyl or an aromatic group. That's where I would start to see things coming into the early 2 in my ppm or in my chemical shift. Having a look at the actual signal itself, it can be hard to read this off. You can come down to the table where you're told that the signal at about 2.44 has 5 peaks. If it has 5 peaks, that means it has 4 neighbors. If I look back to the structure I was starting to draw up earlier, this one here, and I presume that I'm coming from those hydrogens, I said I was nearby a carbonyl, I can see that I have one hydrogen on one side. Another way to potentially finish this off and to have that same sort of coupling would be to imagine 3 more hydrogens on the other, which would ultimately give me my 4 hydrogen environments from the perspective of these methylene protons. That's the only way that I could get, or it's one way that I could get 5. Another is if I imagine from the perspective of a certain carbon, I could have had 4 around like that. That is certainly a possibility of how I could end up with a pentet as well. It doesn't match any of the other data that I have, but it's worth noting that that is a possibility. My last signal to consider, all the way down at about 1 ppm. Again, it's a little bit hard to see. If you're looking closely though, I have 3 peaks on that signal. And it's very, very low down, only at 1 ppm. So I'm far away from anything electronegative. If I have a triplet, that means that I have 2 protons on the carbon next to this structure. And so this is this carbon here and these hydrogens in particular. And they are going through coupling with the CH2 in the middle, which gives me my triplet. Last but not least, I want to look at my peak area ratio and see, is this holding as well? I have a 1 to 2 to 3 ratio between my signals. Well, I have 1 proton here, 2 on that middle carbon, and 3 on my terminal. So everything holds. So we're just going to put all this in and then confirm it and put it together. So in my proton environment, I had a signal or a triplet at about 9.5, likely an aldehyde, that is next door or adjacent to 2 hydrogens. So we know that there's 2 CHs next to that, explaining the outcome of that triplet. Remember, it was an aldehyde, so I also knew that those 2 hydrogens had to be only on one side. I couldn't have split them in both directions. That, of course, would have been a ketone. I see that I have a pentet at approximately 2.3-ish ppm, near something slightly electronegative. With a little bit of electron withdrawal, e.g. an aromatic group or a carbonyl. Either of those are a little bit electron withdrawing, and it can explain that low 2 result. With a pentet, that means that I know if I've only got 5, I've got 5 peaks, I have to have 4 neighbors. And there's 2 ways that I could do that. So either CH, CH3, or 2 lots of CH2. I can imagine either of those would result in 4 proton neighbors. At that point, I actually couldn't be 100% sure. I'd have to combine the other information together. Last but not least, we have a triplet at 1 ppm. Definitely aliphatic, so it's nowhere near anything electron withdrawing. It has 2 proton neighbors. And at this stage, we can also think about our ratios and say that I haven't said it yet, but these are a 1 to 2 to 3 ratio. So likely a single CH, CH2, and CH3 between them. Putting these together, the only logical result really is my propanol, which I knew before when I was even in my carbon, but I can bring that together now and say, yes, this makes perfect sense. And I can confirm that its mass to charge ratio is 58, which goes back and says, yes, that mass spec makes sense. I think about my IR, well, I knew I had my carbonyl, that makes sense. And through all my wet tests, I knew there was something that I could oxidize, knew it wasn't a carboxylic acid, and knew it wasn't a double or a triple bond. So that is me explaining unknown I.